Hello and welcome to the ninth and first episode of Semester 2 after the Christmas break of Delving into Academics. For those who are new here, it's a podcast where various researchers from chemistry, physics and biology are all interviewed about what they're currently working on and their life as an academic. In this episode, Professor Eleanor Campbell tells us about her work to do with C60 and various carbon nanotubes and their applications. I hope you found it as interesting as I did. Okay, so here I am today with Professor Eleanor Campbell. She's a professor in chemistry and she started out doing a Bachelor's of Science in Chemical Physics at the University of Edinburgh, which she graduated in 1982. She then went on to do a PhD in chemistry at the University of Edinburgh again, and then did a postdoc at the Free University in Berlin. When the group moved to the University of Freiburg, she moved with them and stayed there to become an assistant professor there as well. And then in 1993, she moved on to become a department head at the Max Born Institute in Berlin, Germany. In 1998, she was a chair of atomic and molecular physics at Gothenburg University in Sweden. And then she became a chair of physical chemistry at the University of Edinburgh in 2007, then becoming a chair in chemistry in 2013 at the University of Edinburgh again. So thank you so much for coming on the podcast and speaking with us today.
Well, I hope it will be a pleasure. It's nice to meet you, and we'll see what you manage to drag out of me.
Fab. So why don't we just get started with what are you currently researching?
What am I currently researching? Yeah, well, I have, in a way, with part of the research I'm doing now, I've gone back to what I was very interested in about 20 years ago. And we'll find out that I am completely fascinated by a very special molecule, which is carbon-60 or Buckminster fullerene. And this has accompanied me throughout most of my research career. And 20 years ago, we found a way of putting metal ions inside the carbon-60 cage. So for those who don't know, carbon-60 has this fantastic hollow spherical shape, and the carbon atoms are arranged on the spherical surface like the corners of the pentagons and hexagons in a football. So it's very much like a little nano-sized football which has a hollow core. So by doing some collision experiments, we could implant a metal atom inside the hollow core of the carbon-60 molecule, and that changes its properties. So it becomes, if you make a thin film, it becomes metallic, and there are various other things happen. It becomes much more reactive. And back then, one experiment that I really wanted to do was to study this molecule with a scanning tunnel microscope and try to manipulate the atom inside the cage to make a little molecular switch. It didn't work 20 years ago. Nowadays there are much better scanning tunnel microscopes, and we also learned a lot better how to handle this molecule. So I am currently collaborating with a group at St Andrews University, Dr. Schaub, who is an expert in low temperature scanning tunneling microscopy. And we've just succeeded in being able to study this molecule with a lithium inside the cage using his techniques. And we've actually been able to show that by passing a current through the molecule, we can move the position of the atom inside the cage, and that changes the tunneling current. So we can detect the position of the atom, and we have a nice multi-position single molecule based switch. So it's the kind of record on the number of switch positions that a single molecule has been shown to have. And now we're busy thinking how we can take that further and maybe try to convert that actually into a useful nanoelectronic device. And it could, for example, be quite a good way of being able to make a nanoscale random number generator. So we're just busy trying to brainstorm and think about how we could do this and take this further. But it was so nice for me to actually be able to do the experiment that I had wanted to do all those many years ago. I hadn't been trying to do it over the 20 years, but the opportunity arose to collaborate with Reynold Schaub and St Andrews, and that has worked out very nicely. So that's the thing I'm most excited about at the moment, and how we can maybe try to make some useful nanoelectronic component out of this little molecule. Other things that I'm working on, I'm working on a technique that allows us to deposit nanoscale materials cleanly on a substrate, again thinking of a way of making devices that have very nice properties on the nanoscale. And finally, I'm working on making highly porous, lightweight materials based around carbon nanotubes, which is another nanoscale carbon material. And we're collaborating with people in the School of Engineering here at Edinburgh to try to develop new materials that will be good for capturing CO2 from dilute gas sources or from the atmosphere. So a wide range of different things.
Yeah, see, and it all sounds so exciting, and the fact that you're working on a couple different things, but it all seems to feature, I guess, these carbon nanomolecules.
Yeah.
So is there something special about carbon nanomolecules that make them really interesting to study? What are their sorts of properties are you looking at whilst you're doing all this research?
Yeah, I mean, it's a fascinating material. As I say, I got started with those just after I finished my PhD. So carbon-60, this football-shaped molecule, was discovered in 1985, which was the year I graduated with my PhD. And I was, by chance, I kind of landed right at the beginning of that research activity, which is another story that we might come to. and I just became, C60 itself is a molecule with very special properties. It's a very stable molecule. It has this nice hollow shape, which I think is just beautiful. And I've always been very keen on football, so it merged my interests very nicely. So I'm missing an important match right now. So it's a very resilient molecule, and in fact C60, we now know with relatively recent work, is present in space in rather large quantities. And it's actually a young lecturer who I now managed to persuade to come to Edinburgh, who did a beautiful spectroscopy experiment at the University of Basel, which was able to prove that carbon-60 contributes to what are known as diffuse interstellar bands in the interstellar medium. Mm-hmm. And these are a whole series of sharp molecular absorption lines that have been known for about 100 years, but nobody has been able to identify what molecules are responsible for them until Eleanor Campbell, no relative, who's the young researcher who's now here, was able to show by comparing laboratory spectroscopy with those observed lines that actually 5 of these lines are due to the C60 positive ion. So it's the first molecule that's been identified as contributing to these features. And they were able to work out roughly how much C60 is present, and it's a surprising large amount. And they can survive in space because of the very special properties that these molecules have. It's very, very difficult to break up a carbon-60, especially if it's in vacuum and there's no oxygen around to react with it. So it can really survive for ever, basically, in many of the conditions that are around in the interstellar atmosphere. So we didn't know that at the time when we started with carbon-60, but now that's actually, I think, it certainly got me excited again to go back and do fundamental gas phase studies on the carbon-60 molecule, which is how I started with my carbon materials way back in the late 80s, early 90s. So I find these molecules, the fullerenes, fascinating. There's a whole family of them, not just carbon-60. And then from the fullerenes, if you think about growing those, so expanding the cage, you can blow them up like balloons, but actually what they like to do is expand along one dimension, and they grow into what are known as carbon nanotubes. So in the 1990s, it seemed almost like an obvious thing to get interested in the carbon nanotubes. And they are also very interesting. So these are the strongest fibers that have ever been made. And I've always loved science fiction. And one great thing in some of the science fiction novels is a space elevator. I don't know if you read science fiction, but this was a wonderful idea where you have a cable that's attached to the Earth at one end and attached to a satellite at the other end. And you can use this to get payloads with a very low energy cost into space. So you shoot them up the cable, and then when they reach the top of the cable, you cut the connection and they'll fly off into space. But to do that, you need a cable with very, very particular properties. It has to be incredibly strong and all kinds of properties. The carbon nanotubes are the only material that, in principle, could be used to make a space elevator cable. I think that's really cool. Nobody has made the space elevator cable out of them, but in principle it could be done. And they have very interesting electronic properties. So, I mean, recently, particularly in the UK, there's been enormous interest on graphene, a single layer of carbon atoms that you can get from graphite, which got a Nobel Prize to two people in Manchester a few years ago. But actually, the carbon nanotubes have basically the same properties because they're just a single sheet of graphene that's rolled up into a cylinder. So before people had the single layer of graphene, we were studying the electronic properties of the carbon nanotubes, which are very similar. But you have the advantage with the nanotubes that you can cover a whole range. So you can have semiconductor nanotubes. You can tune the band gap of the semiconductor by changing the diameter of the nanotube. And you can have metallic nanotubes, which are ballistic conductors of electrons, which means there's no resistance over a small scale, and quite a good few nanometers or micrometers even. So you can use these little nanotubes to make nanoelectronic components. So that's something I spent quite a few years doing, mainly when I was working in Sweden, because there was a very fancy nanofabrication facility. So we were able to make little transistors on the nanoscale and little nano-electromechanical devices out of the individual nanotubes, so make little switches and see how they move and how the properties influence the behaviour. So following on from very kind of fundamental gas phase studies of C60, I ended up doing nanoelectronic devices for a number of years. Quite a different area of research. And then moving to Edinburgh, I couldn't really do the nanofabrication anymore, and I was in the chemistry department, so then I had to do something more chemistry related, and that's where the carbon capture materials came in, and the interaction with the engineers here. But carbon has this fantastic property that it is an incredibly flexible atom. So it can form all these different structures. And all of these carbon nanomaterials that I've been talking about are all based on the graphite-like bonding that carbon has, where you make these flat planes with sp2 bonded carbon. This is a pod, I can't show you a model, right? There's no point in that. But in the fullerenes and in the nanotubes, you introduce pentagons into the hexagonal structure that you have in graphite, and that makes them curl up and form these closed structures. And it turns out, and mathematics comes in here, there's Euler's theorem of polyhedra, which tells you that if you have 12 pentagons and any number of hexagons, you can form a closed polyhedron. And that's exactly how the fullerenes and the nanotubes are constructed, which is very cool. And you have to have an even number of carbon atoms. Another interesting thing. So you can't have a fullerene with an odd number of carbon atoms. So you can get these sp2 bonds, which are the most interesting from the nanocarbon point of view. Or you can have the sp3 bonded carbon, which gives you diamond, which is a very different structure. It's a three-dimensional structure. It has very different properties to the graphitic-like bonding of the other materials. Or you can have sp hybridized, which gives you a long chain of carbon atoms. But that's very unstable if you go to more than 2 or 3 atoms. But actually you can isolate that by putting it inside a nanotube. And you can use nanotubes as little test tubes to study much more reactive materials that are kept inside them and isolated from the environment.
Wow.
And carbon's amazing.
Yeah, it seems to relate to so many different...
It does, and there's an enormous number of potential applications based on the properties of the carbon materials. Yeah. And we haven't even touched on organic chemistry, which is also carbon basically with other bits and pieces added in.
Yeah. It seems like carbon can pop up everywhere.
It does pop up everywhere, right?
Applications and uses. So through your research and your studies of different carbon molecules, what types of applications are you potentially looking at for the types of molecules that you're looking at?
Fullerenes, the work we do is basically, we might see where our little molecular switch goes, but if that's an application, it's many, many years down the line. From the fullerene point of view, it's mainly the fundamental interest in exploring the properties. Now, more recently, it's how it ties into astrochemistry, because people never really thought about the consequences of having these big carbon molecules out there. Now we know they're out there, it's opening up many, many questions about how that influences the chemistry of space and potentially even life being developed. So I'm also beginning to collaborate with Professor Coquelle in physics. I hope you're interviewing him, or have already interviewed him.
He's been on the podcast. He taught me about astrochemistry and the potentials there as well.
Yeah, so we're talking about how fullerenes might fit in to these things. So that's kind of an application, I suppose, but not a real life useful application. Carbon nanotubes, when we were working on the nano devices, we had a fairly long-standing collaboration with the Finnish company Nokia, and that was in the days when they had lots of money. They then ran into financial problems, I hope not because of the collaboration with us. But they were really interested in having a nanoscale device which they could tune to allow specific radio frequencies to pass through, and to incorporate that in mobile phone technology and so on. So they were very interested in our little suspended carbon nanotubes that we could make that will vibrate with a high frequency. And you can tune the vibrational frequency by applying a voltage to an electrode that sits underneath the nanotube. So we worked on that for quite a few years with Nokia. The devices worked very nicely, but the big difficulty is kind of the next stage in actually having a fabrication process that can produce millions of these and have identical properties. And that's where it became too much like engineering for me to follow up. And that's when I came back to Edinburgh. But that was an interesting period for me to collaborate with the people in industry and really see things from their perspective and what was important for them, and try to bring two very different approaches together to try to do something useful. And it was very challenging. And you can't buy one of my nanotube devices, but I think we learned a lot about how to make these, how to manipulate them. And we're able to show, so we have quite a number of patents with Nokia in actually showing the kind of devices that could be made based on the properties that we were able to demonstrate. So that's the closest I've come, I think, to real application with industry. Nowadays we're working on trying to develop useful porous materials for the carbon dioxide uptake. And there I don't have a concrete industrial collaboration there, but this is something that has a clear goal. And a more short-term goal probably than the nanotube devices that we were working on before. and that also has some challenges. But again, it is quite nice. I mean, I get most excited about the fundamental side of things, but it is actually nice, and I think the students like very much working on a project where you can see, in the not too distant future, there's really something useful that could come from this.
Yeah, that sounds really exciting, and the different applications, and yeah, I guess part of academia and research is more looking at the fundamental properties, studying their properties, rather than maybe how it can be applied in industry or the real world. Mm-hmm. But with you talked about studying porous materials and with carbon dioxide uptake and such, and that has been a very talked about issue, especially when relating to climate change and greenhouse gases and such. Do you see it kind of having an impact there, or is it more to just research how these materials could uptake?
I mean, I think what we can contribute most to this with our background is the production of the materials and testing how good they are for taking up carbon dioxide from gas streams that are similar to what you might have from industrial plants or maybe even from the atmosphere. And where we're working together with the engineers are developing systems where these materials can be incorporated that could be used by industry. So they're designing a special kind of system for using these materials in a kind of rotary wheel setup where the materials will absorb CO2, they will then kind of turn around and they'll enter a phase where the CO2 is then released and then captured in perhaps another material and then concentrated and then finally stored in a gas bottle or piped into a lab where something useful will be made from it. So we are, certainly from the engineering aspect of those collaborations, we are really trying to make something useful that can maybe be packed into a shipping container and placed at a small industrial plant. But we don't have the skill set to do that side of things, but the engineers do. It comes together very nicely.
Yeah, and it's really good for the sciences, especially by doing these podcasts. I'm really seeing there's so many connections between the sciences, and I think nowadays it's you can achieve quite a lot from collaboration with chemistry and engineering and what can come from that is quite an exciting field.
Yes, I think the science has become increasingly collaborative. It's much more than when I was starting out. So it's very difficult now as a scientist to just stick in your own little lab with a couple of students and do something interesting. It's become much more collaborative and interdisciplinary activity, which makes it a lot more fun, I think.
Yeah, absolutely. And I guess you have the opportunity to learn about a different science that you may not have considered.
Oh, absolutely. I mean, when I started out, first of all, I would never have thought I'd be working with large carbon molecules. I started out doing very fundamental research, colliding atoms, alkali atoms with small molecules like methyl iodide, and looking at how energy was transferred in those collisions, the molecular beam collisions. So I was doing atomic collisions, molecular collisions. There's no way then I would have thought I would be doing something like nanoelectronics. Yeah. Or carbon capture, or even taking a femtosecond laser and seeing how that interacts with a C60 molecule. And I think I've been fairly lucky. I've moved around a lot, as you said in your introduction, and everywhere I've been, there have been different opportunities that have opened up and kind of made me go off into a slightly different direction and learn new things, meet new collaboration partners. And it's just recently, in the last few years, I've kind of gone back to my C60 again.
Yeah.
But that is also opening up new, because of this new astrochemical aspect, I'm learning a lot about astrochemistry. So even sort of by going back to what I did 20, 30 years ago, to a large extent, it's opening up new horizons again.
Yeah, and I guess with developments and such it can, and it will kind of keep going. Like astrochemistry, I know Professor Cockle, it was like astrobio wasn't really a thing when I was a student, and so it's probably very nice for you, especially to go back to that first interest and to study these types of molecules and to see their different properties and how they can be used. It sounds very exciting.
It's nice, and I can actually make use of some of the early experiments I did to feed into the astrochemistry understanding, which is also nice.
Yeah, absolutely. And to kind of also take it back to your research on these types of molecules and maybe linking it to astrochemistry, are you doing any types of experiments to figure out why these chemicals are so abundant in space?
We're not actually doing experiments on that at the moment. I would like to. It's a question of money. I mean, what I'm trying to do at the moment is to think what kind of experiments should we be doing in the lab to understand that, because we don't really understand how they're being formed. We know how we can make carbon-60 in the lab, and there are different ways of doing that. You can do it from a bottom-up way, where you just make a lot of carbon vapor at the right kind of temperature, and it will end up, as it cools down, it will end up as C60 or C70. So it grows from small carbon molecules coming together, merging, and building up to the fullerenes. You can also make it if you take a large hydrocarbon molecule that's got more than 60 carbon atoms, and you hit that with a laser, you'll get carbon-60. So carbon really wants to make this form. It feels comfortable, it's very stable, and there are many ways that this will pop out. As long as you've got enough energy to allow the carbon atoms that you have available to rearrange to form the C60 cage, it will do it. But what's happening in space? We don't know, right? Because the conditions are very, very different from the conditions in the lab. And the time scale is, of course, so different, right? So some people think possibly it can grow from small carbon molecules and build up, and then you have some fragmentation steps and so on, and eventually the C60 emerges. Others think that you have a large polycyclic aromatic hydrocarbon molecule which gets hit by a cosmic ray, and then you get C60 forming. But then, of course, you have to answer the question, how does the large polycyclic aromatic hydrocarbon molecule form in the first place? Right? So we simply don't know. And we don't really know where they're being made. We know where we detect them, but they might be being made somewhere differently, and they're only excited, or we see their absorption spectrum in particular regions, but they might have travelled from somewhere quite different to get there. So lots of puzzles, which is great.
So it sounds like a lot of questions.
There are lots of questions, And one question, very important question, is how are they being made, and how can we test any hypothesis about how they're being made in the laboratory? And that's not so easy. What I would like to do is set up a spectroscopy experiment to measure the high resolution spectrum of the neutral molecules, because that's what astronomers are really needing at the moment, to see if they can plot out other positions and get more information on where fullerenes are, and that might help us understand how they're being formed. But we'll see how that happens. And with Eleanor Campbell here, who's the guy who did the experiment in Basel, he's continuing to do the spectroscopy on the ions, and he has his lab all nicely set up here. He brought all the equipment with him from Basel, and he's starting to look at some very interesting molecules in his ion trap. So he's very much on the astrochemistry, spectroscopy side of things. So it's very nice to have him as someone to talk to and to brainstorm with about the experiments that we should be doing.
Yeah, absolutely. And I guess from there, like you can start answering all these questions
hopefully,
you have. And maybe even gather some more interest as well into the topic and into these kind of questions, because I think that's also part of it, bringing to light these sorts of questions and kind of posing them.
That's right, yeah, that's right.
So also about you mentioned the C60 molecules and that you put a lithium. and now it acts like a switch. In nanoelectronics, you can use this. How exactly does it act as a switch? And also, what do you mean by switch? Do you mean like on, off, or?
Yeah, it could on, off, but it has multiple positions. So we've demonstrated 14 different positions, right? And that comes about because if you think about the shape of a football, think of the old-fashioned football with the black and white patches. Right? The black patches are pentagons, and the white patches are hexagons. If you count the corners, there are 60. Right? So you have a black patch surrounded by 5 white patches, and that builds up to give you the football. So if you consider the hexagons, there are 20 hexagons in a C60 cage, 12 pentagons, 20 hexagons. When the lithium is inside the cage, it's more comfortable being shifted towards a hexagon. So it doesn't sit in the centre of the cage, it sits off-centre next to a hexagon. And when you put this molecule on a surface, which is what we do in the STM, scanning tunneling microscope experiments, the lithium sits next to the top hexagon. So you sit the molecule with a hexagon down on a metal, and at the top there's another hexagon, and the lithium is just beside that one. Now you can switch the position. So if you have this sitting there, you can measure the current, the electrical current that will pass through this molecule when you apply a bias with your STM tip. Now if you just give it a quick pulse with a higher current, what happens is the lithium moves. And it moves, so you're coupling energy to the lithium inside the cage, and it actually rattles around the cage, and then it comes to a stop against another hexagon. So you have a statistical position of the lithium after your switch. So you can't say to it, okay, I want you to switch from the top position to the position on the right-hand side of the centre. Right? Yeah. You can't do that, but you'll say, okay, lithium, now you're moving, and it moves randomly. And then it stays where it has moved to. And if you measure the tunneling current through that molecule with the moved lithium, it's different from the original tunneling current. Right? So you can detect that the lithium has changed position. So you've switched the lithium position, and you've changed the current that passes through your little switch.
Okay.
Yeah?
Yeah.
So why I said this could be good for a random number generator is because of the statistical position of the lithium, and you get statistical currents being produced, for 13 or 14 different positions of this lithium that you can detect. And I think we're still working this out, right? But I think this could be a nice little random number generator.
Yeah, it sounds really cool how you can.
And there may be other fullerenes like this. We call these endohedral fullerenes with something inside the cage, where you might actually be able to design the system to be able to switch specifically to different positions. So switch from position 1 to position 3 and detect a current, switch it to position 2, detect another current. And that could be useful for kind of standard switches, as it were, in electrical circuits.
Wow.
But again, that's work we need to do to design the system, see if we can make that particular molecule, and then test the ideas if we can get the specific switching. But the nice thing about using these fullerene molecules for switches is that when you switch them, they don't change shape. In most molecular electronics switches, the molecule changes shape. And that makes it very difficult to incorporate in an electronic circuit. But these don't change shape, and they're very stable, and they'll just sit there. You're not going to fragment them if you pass too much current through. Well, reasonable amounts of current. So they're much more practical if you can find a way of fabricating millions of those and putting them exactly where you want them. That's not so easy.
It sounds like there's still a lot to explore and a lot of, experimentation to be done on these types of molecules. So you kind of touched a bit about where you want this type of research to head and the possibilities that could come from this. But what are the next steps for this type of research? Have you got something like another experiment in place, or where do you see these types of molecules going in the future?
Yeah, well, I would like to, with the switch, I would like to try and push that as far as I can. That needs the fancy scanning tunneling microscope that we don't have here, we have in St Andrews. What we can do here is a gas phase spectroscopy that kind of gives us an idea of where the particular states are that we need to cause this switching to take place, and to explore the mechanisms behind it, which we don't really understand yet. So that we have an apparatus set up there, and I'm actually looking for, an ambitious PhD student to take this on and do STM work and do some theoretical modelling to accompany it. So if you know of any, please send them in my direction.
So yeah, keep your ear out.
Could be a physicist, I'm quite happy for physicists. Could be a chemist, whatever. So anyway, I hope to do that, and we have a collaboration which we will start with a theoretical group in Singapore who are very keen to do some calculations to understand this switching mechanism. So it will be tying down the mechanism, once we understand how it's happening, designing molecules that can give us different switching possibilities and see if we can test that and understand how it's happening. So for me, that's where that's going. On the astrochemistry side, it has to be spectroscopy. So we really have to develop some high-resolution spectroscopy experiments to really take that forward and discuss much more with the astronomy community. What signatures should they be looking for to detect these molecules? If we can detect other fullerene-based molecules but not the C60, where do the astronomers need to look, and what sensitivity would be needed to detect them? So I think these are the important things on that side with the fullerenes. But things pop up. And I didn't really think I would go back to making a fullerene switch. That was just a chance thinking that, well, maybe these guys in St Andrews can do something here. Right? It wasn't really planned out in any way. And very often unexpected things arise from the fullerene or the carbon type activities. And I mean, most of what I have done has not really been planned out in great detail beforehand. It's just happened.
It seems to have worked out very well.
Well, it has. I think I was very lucky with this because I as I say, I stumbled across the fullerenes by chance. I was doing something totally different. I had a project when I started in Freiburg, which I was doing very fundamental collision experiments on one side. And then on the other side, the group decided to kind of expand and bring in more research funds by doing something a little bit more applied. So I was given the task of finding something that we could do that would be more applied. So I remember I went to the library. In those days you had to go to the physical library. And I kind of flicked through a few journals, and I knew in the group we had mass spectrometers and we had lasers. So I saw that people were interested in laser ablation. So that's using an intense laser to make holes in materials. And in particular, IBM was interested in using a laser to write structure in polyimide, which was the insulator they were using in their computer chips. And they were having problems with this because they were getting carbon deposited on the polymer when they were using the laser to write these micron-sized structures. So I thought, okay, this is something we can look at. And nobody at that time was kind of doing this in situ, using a mass spectrometer to detect what was being produced from the laser ablation process. So I decided to set that up. So I had everything there basically that I needed. And we were looking at the mass spectra coming from this ablation process, and we were getting lots of hydrocarbons and complex molecules with nitrogen and oxygen and everything in there. And we were kind of studying this and seeing how this depended on the laser intensity and the type of polymer and so on. And it was quite interesting. But then one day my PhD student made a mistake when he was setting up the experiment. And instead of measuring a mass range from 0 to about 300, he measured from 0 to 3000. And what we saw was a wonderful mass spectrum of all the fullerene peaks, and a nice strong peak at 60 carbon atoms. And this was just 3 years after the C60 had been discovered. So it took us a while to work out that that's what we were seeing, right? Because you have, with carbon-60, you don't just see one peak at the mass of 60 times 12, which is the mass of carbon, because you have a carbon-13 isotope there. So you get a 720 mass peak, 21, 22, 23. And we were a bit puzzled by that. We've got hydrogen, so what kind of molecules would these be? And we just didn't think that you've got 1% carbon-13 in natural carbon. And it was actually somebody else that pointed that out and visited the lab. And I was showing him this mass spectrum and was like, we don't really know what this is. We've got all these great, large mass molecules. And he said, have you thought about carbon-13? So I went away and worked out the ratios and simulated exactly the peaks that we were seeing. So it was pure carbon. And then I kind of looked back on this C60 discovery paper, and that got me hooked totally. And that's when I started working with C60. But it was completely by chance.
Yeah, that's such a cool story how you managed to find the one molecule that you've been fascinated with all this time.
And it was a mistake by a PhD student that got me there. Yeah.
The one-time mistakes that have paid off.
Yeah. But that actually happens, quite often.
So you do sound really passionate about this molecule and your research on it and other types of carbon molecules. What is it about being a researcher that fascinates you so much?
It's just, I don't know, I think it's just the curiosity to just learn more about the world, right? And liking to solve puzzles. And as an experimentalist, what I love, I don't get to do it now. Most of my time is spent sitting on committees these days. But what I really loved in the early years when I was setting out and building up my group and my research activities was sitting down and thinking, what kind of experiment do I want to do to probe such a property? And designing that experiment, drawing it up, giving it to a workshop, have them actually build the piece of kit, setting it up in the lab, testing it, and then doing the experiment. So the whole range from thinking what could we do in the lab, designing it, building it, and then getting some nice new results that nobody else could get because nobody else had built your piece of apparatus. And that for me was just fantastic. And I built lots of crazy apparatus when I was working in Germany particularly, because they had fantastic workshops in the university departments. I was in physics departments there were very good workshops. And I had the opportunity to build what I wanted. And I really took advantage of that. And it was just fantastic, right? And being able to sort of have the freedom to kind of follow what you think is interesting. It's quite difficult. It's getting more and more difficult because funding for research tends to be tied to very specific projects. But that was what I loved. I loved just following my curiosity and taking it as far as I could.
Yeah, and it sounds quite exciting, and I think that's what drives the majority of scientists in general. Just the curiosity to find like a topic and be like, oh, why? Like, and all these sorts of questions, and then finding the answers. And it sounds so cool that you could think of these experiments and then build the apparatus. And yeah, as you said, no one has this apparatus, and you can just do the experiments. It sounds so cool.
And it was. It was a lot of work, but it was it was a lot of fun. Yeah.
Yeah, good, I bet. Yeah, so I guess then from undergraduates, you say it's kind of, I guess, a different climate or a different, well, academics nowadays, it's different. It is harder to get funding, and many undergraduates have heard about this. It might put them off, or they just might still want to follow their own curiosity and become an academic. And so do you have any advice for undergraduates that may want to go into research in the future, or maybe they're not sure on what they want to do and they're just kind of studying this, or studying chemistry or studying physics, or whatever they're studying just because they like that subject?
Yeah, I mean, it's a kind of difficult question. Things are tougher these days. But they were also quite tough when I started out too. There wasn't much funding in the system, I remember that. I remember doing my final year project and I kept hearing moans and groans about no money and blah, blah, blah. And then I had the opportunity to go to Germany and it was very different there. But I think taking that opportunity is what turned me into an academic. I wanted to do a PhD because I really loved being in the lab and I just loved that whole thing. And even from when I was at school, I can still remember the first day we had science labs at school. It was when I was in first year secondary school. And up until then, I had been most interested in history and English, thought I might be a librarian. I walked into the science lab and started doing a very trivial little experiment. I don't even remember what it was. And I thought then, just doing that, thinking about the experiment, doing the experiment, learning something from that's what clicked with me. And I said, I really want to be a scientist. And that was that first day in the lab, hands-on, doing an experiment. And I just went with that, although I was, people were telling me you have to study medicine or you have to do this, that, or the other. I studied chemical physics, not because I had a career in mind, but because I was really fascinated by chemistry and physics, and I really wanted to know more. Then the next decision is PhD. Do I do a PhD and go on the research track? And I really wanted to do that because I simply loved being in the lab. I absolutely loved my final year project. And I thought, well, okay, I really want to do this. I love the solving the problems in the lab and doing something that nobody else has ever done. I really loved that. No matter how useful it was, I would do something that nobody else has ever done. So I did the PhD, and that was a fairly easy decision. And then the postdoc is a tough decision. Do you go into industry? Do you go and do something very different from science, but you have that good scientific background, which helps you with all sorts of things, right? You learn how to problem solve, how to work in a team, all kinds of generic skills which are incredibly useful. Or do you take the plunge and try to stay in academia? And at that point, I ended up doing a postdoc to give me a little bit of breathing space and to earn some money for very personal reasons that we won't go into. And I still really didn't think I would be able to follow an academic career and I would be able to become a professor. Right? I would have liked to have done it, but I didn't really think it was possible. And I didn't think it was possible because I looked around at who were professors and lecturers, and they weren't anything like me. Right? They were predominantly males, elderly males who had been to Oxford and Cambridge. Right? And I just couldn't relate to them. So it wasn't something that I had as a goal. But I thought, okay, I don't really have to depend. I'll just go off and do what I want to do for as long as I can, and then I can always get another job or go into teaching. So I decided not to worry about it too much. And I had the time in Germany and was able to then follow that. But it was not necessarily an easier time to be a scientist in the UK or even elsewhere. Germany was fine, so I was lucky. Nowadays, there are more pressures, I think, on people. And of course, there's the university fee situation and building up debts. And I can understand that people are really thinking much more than we ever did. I really need to get a job. I need to earn some money. I need to have some kind of security. I would say to people, if you are passionate about science, do a PhD. Right? You'll get funding while you're doing your PhD. Do something that you are really interested in. Or if you really just want to do research but you're not sure whatever you decide to do or whatever position you get, you can make that interesting. Because when you dive into research, when you're really focused on a research project, anything can be interesting. It doesn't need to be a C60 molecule that suddenly, gets your pulse racing. You can turn any research project into something really interesting because you're digging into that. You always have the potential of doing something new, something different, and bringing your imagination and your creativity into it. So you just go with the opportunities. And if you're passionate about doing this, if you want to do research, go for it. And don't worry about what's going to happen 5 or 10 years down the line. Things will happen. It might not work out. You haven't lost out a lot by that. You spent a few years, doing something that you think you're going to love doing. Might not work out. But you have developed skills during that time which you can apply in any field, in any walk of life. So it's not, wasted time. If you do a PhD or you do a postdoc after that for a year or two and don't end up in the universities. There are not enough university positions for everyone who does a PhD. And you just, go with the flow. And don't be afraid to do, slightly crazy things along the way if you really want to do them.
Yeah, that's really great advice. It's quite comforting. Don't worry about the kind of.
I mean, that's easy to say, and it's very easy for me to say. Here I am sitting here as a big professor, blah blah blah. But it wasn't always easy.
Yeah, absolutely. And you have worked for this professorship.
Yeah, and I've worked hard, but if you're doing something you love, it doesn't seem like work.
Yeah, absolutely.
Right? So it's your hobby and everything rolled into one. Yeah. And you don't really mind putting in a few extra hours here and there.
Yeah, absolutely. And that's especially my parents also say, do something that you love, because you've got to do it for so much of your time. You've got to make it something that you love. And
yes.
As you say, if it's a hobby and you're not going to mind working loads on it.
That's right.
So that was really great advice, really comforting insights. So unfortunately we've come to the very last question of the podcast, which is, do you have any sort of recommendation of a book or an article or paper for us today?
Well, I thought a little bit about what influenced me. I'm going back quite far here, and I'm going back to my early teens. And this was the time when I was just discovering, experiments in chemistry labs or science labs. And it's also when I discovered my love of science fiction and all these kind of things. But one book I read at the time, and I basically read through all the books in the local library, I think, while I was at school. One book which I think had a big influence on me, and which I would recommend to people if they haven't read it, is the Biography of Marie Curie. And it's the one written by her daughter, Eve Curie. I think there are probably better biographies of her now. But this is quite a meaty tome. It's quite a thick book. I read that when I was about 13, I think, 13 or 14. And it was an eye-opener to me. And I mean, Marie Curie, because I didn't know about her when I read the book. It was just one of these, the next one on the shelf in the library. Because I had none of my family were scientists, or there was no kind of role model or anything there. And I read this book, and I thought it was a fantastic story. And it kind of made me see that, these famous scientists are kind of ordinary people. And that's not always something that's maybe obvious, right? We're all humans. We all have our faults and our good sides and so on. And I was just fascinated by this story and her ambition and drive to get where she was, and the woman to get 2 Nobel Prizes early on. And I'm absolutely amazed by her. And I think that inspired me. And it gave me the feeling that I'm not totally wasting my time wanting to study physics and chemistry. Because that's kind of what I was wanting to do, but people were saying, you can't be a scientist, go and be an air hostess, or which somebody actually told me at some point, or a PA. That was the careers advice I was given when I was 14. You should go and be a personal assistant. And I listened to that. I thought, well, wait a minute. Why shouldn't I be the one with the personal assistant? But then knowing that someone like Marie Curie had, kind of struggled and really, wanted to do her physics, I think that was a big help and a big inspiration. So I think that's the book that probably has inspired me the most when I think about it.
Yeah.
Another one I loved, also biography, is the biography of James Clerk Maxwell, who's a great hero of mine.
Yeah.
And, he's also a normal person. And what I loved about James Clerk Maxwell was the fact that he wrote little silly poems. He took the sort of traditional songs and wrote new words to the songs. And that's actually something I love to do too. I thought, we've got something in common. But seeing that he was someone with a sense of humour and not this godlike genius figure,
Yeah.
And I think that's important. I think it's important that people realise that, these are ordinary people.
Yeah.
Right? And if they can do it, you can do it.
Yeah, absolutely. And they're really good role models. At the end of the day, every scientist is just a person.
Yeah.
So it's, they're brilliant recommendations to kind of get a real sense of the person behind, because you hear about Marie Curie quite a bit, and you hear about James Clerk Maxwell and their work, but to get a sense of the person behind that work will be really inspirational.
Yeah, I think that's a good thing to do. People don't read books anymore, but go and pick up some of these biographies.
It's just like 2 books that they read in their life. These two.
Pick these 2.
Absolutely. So thank you so much for coming on this podcast and chatting with you. It's been absolutely brilliant to gain insight into your work and how you came to be a professor and an academic as well. And so, yeah.
Thank you. It's been a pleasure.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another episode.